Okay, thank you. I decided to summarize my title furthermore. So, hi everyone, I'm Vatsal Panwar. I'm a fourth-year PhD student at University of Amsterdam. And essentially what I'll be talking to you about is the challenge of combining multi-epoch observations of exoplanet atmospheres. So one of the methods to study transiting exoplanet atmospheres from ground, as has been mentioned previously in the symposium, is to use ground-based multi-object spectrographs like GMOS or Force2 or Magellan, for example. And the idea is that you observe your star with the planet and another comparison star in the field of view of the instrument, or multiple comparison stars, and use these comparison stars to correct for the systematics commonly affecting both the target and the comparison star. So here is an example of a transit that was observed by Gemini GMOS of HATP1 using Gemini GMOS. And you can see that in most cases, you can actually obtain precisions almost comparable to what you would get from HST TESS. But what I would like to do today is to just revisit this, the basis of this technique. So here is an example of one of the favorite active host star planet, WASP-19, a transit observed by Gemini GMOS. And what you see here is a lot of systematic effects evident both in the comparison and the target star. One of them is the air mass itself that affects both the stars over the whole time scale of the transit. So for example, 3 hours for WASP-19. And in particular, in case of GMOS, you have this shutter effect that affects alternate exposures. Like you almost see a sort of an odd even pattern. And if you go ahead and just approach this by a simple normalization of the target by the comparison star, there is an intrinsic problem there because your comparison star could itself be variable, which would actually imprint an effect on the final transition spectra. And even if the comparison star is not variable, you would still be adding systematics which are not affecting both the stars commonly. So what I have been doing is basically going to the root of this technique and developing a method to use the comparison star itself as a sort of prior to fit the target star. And what this does is it lets you extract the information about the systematics commonly affecting both the stars, encode that into a Gaussian process model, and fit your target star light curve without doing any sort of normalization. So I applied this method to one of the 8 transits that we observed for WASP-19, and just comparing it to the old or conventional method of just simply dividing the target star by the comparison star, and from the new method by using the comparison star as an input to your GP model, we already see that we obtain a better precision by almost a factor of 2. And validating this method against synthetic light curves. So what I did is essentially just test how well this works if I take a synthetic light curve with known transit parameters and apply both normalizing by the comparison star and just using the comparison star as an input to my Gaussian process model. And what I find is that the new method of using just the comparison star as an input to the Gaussian process model in the posterior shown red performs much better in retrieving the original transit parameters. And this becomes really important for a case of WASP-19. So here is an example of a one sector TESS light curve observed for WASP-19, where we see a clear 2 to 3% peak to peak variability in the bandpass in which we're trying to characterize its atmosphere. And the question is, how does this actually reflect on the planet spectrum itself? So what I have been working on is applying my new method to about 8 transits of WASP-19, and just using the information from the white light curve itself without using any of the comparison star. I simply fit the spectroscopic light curve. So I use the white light curve noise model as an input to my noise model for individual spectroscopic light curves. And the strength of this approach is that it avoids any contamination from, say, variability or non-common systematics from the comparison star. It lets you observe or measure a sort of absolute transmission spectra because you're not doing any sort of common mode correction. And it lets you propagate the uncertainties from your white light curve noise model to your spectroscopic light curves within the framework of Gaussian processes. So how does it portend for the spectrum of FOSS19? Here is one of the one transit observation from HST that was observed back in 2013, where they observed a non-muted water absorption feature. And at these temperatures, as has been investigated for this planet, you should be expecting absorption due to gas phase TIO in the optical bandpass. So just looking at one of the transmission spectra from one of the 8 transits that we observe, it looks like it might be the case that we might be seeing absorption due to TIO. But when I just plot another observation, it looks like it might be an effect of just unocculted spots. So just to mention that we do not observe any clear spot crossing events as has been observed for this planet before. And another transit looks like it might be more consistent with just the facula. So to just go further and do a sort of first order analysis of how, as we already know that the star has spots and faculae, how that might be reflected in our spectrum. So here's the stellar contamination factor that you would observe for WASP-19. So one of the works by Nestor where they observe occultation of star spots and faculae, as Brett also mentioned before. I use the properties consistent with those observations and also consistent with the variability of the star in the optical bandpass, and just simply fit a linear slope to each of the epoch observations, the transmission spectra that we get, and compare that with the absolute level of the transmission spectrum. So what essentially you're seeing in the plot here is the linear slope of the individual observations going from all the way to minus 0.6 to 0.6. So it's with respect to the units of wavelength. But towards the right, what you're seeing is the effect of the faculae. So you have a positive slope, but offset towards the negative side. And on top left, what you're seeing is the effect of spots, but so positive offset and negative slope. And this is kind of evident in all the 8 transits that we observe. And when I compare this with what we observe from TESS, so TESS has observed about 26 transits of FOSS-19. We kind of see this change in the white light curve transit depths with respect to just the normalized out of transit flux for each of the transit. Which kind of raises the question that could we just simply combine these observations? Could we just simply combine these transmission spectra? And I think, so on the talk before me, as they emphasize, is really using simultaneous or other measurements of the stellar of photospheric and chromospheric heterogeneity properties would actually be needed to be able to correct these effects before you can just simply go ahead and combine these spectra. Just to mention that in the individual observations, we do not notice any strong absorption features due to gas phase TIO. So just accept the slope. We do not detect any strong absorption features. So this, I'll leave you with my conclusion. Essentially, we have developed a new method to analyze the ground-based MOS data, which provides a more accurate and precise estimates of wavelength-dependent transit depths. And it really raises the concerns on how reliably we can combine transmission spectra observed over multiple epochs. Thank you.
Thank you. There's one question for you. Could your GP analysis be described as a type of a spectral smoothing of the comparison spectrum?
Well, that's a very interesting question. So I think in terms of, actually, I would like to ask, spectral smoothing, is that, I understand correctly, is that with respect to the spectroscopic light curves, or just corresponding to the white light curves? I'm sorry.
I don't know.
So it's my question. This is Drake Deming.
Hi.
So if you divide the comparison star spectrum, the target star spectrum by the comparison star on a point by point basis, you would be adding photon noise from both stars together.
Yeah.
But if you smooth the comparison star in wavelength, then that would reduce that additional photon noise from the comparison star. So that's what I'm asking. Is the GP just a sophisticated version of smoothing in wavelength?
I see. So in the way I have been using it is to only use it for the white light curve, because I add up the noise or the systematics common between both the comparison and the target star light curve, and then use that sort of correlated noise information that I have to fit the spectroscopic light curve. So I do not use the comparison star spectra at all when I'm fitting the spectra.
Okay, thank you.
Okay.
Okay, there's no more questions. Thanks.